actually. Can you guys see us as well, or is it just the slides?
We can see you actually.
Oh, you can. Okay, great.
Awesome.
Let me see if I can. Well, we'll see if this works. Okay, awesome. Let us know when you get started. Is now good?
Yep, this is good. We can start.
Okay, awesome. First off, thanks, Abhinav and Daniel, for the invitation to come and talk a little bit about what we've been doing here at Meta on implementing this PyTorch version of distributed shampoo. So I'm Michael. This is my collaborator Shintaro. So we're actually part of the AI and systems co-design team here at Meta. This is a team that sits in the infra organization at Meta and sort of operates in between sort of FAIR and sort of this pure research and sort of production teams that you would think of in like Gen AI or ads. So we really are the team that's in charge of doing sort of the applied research and scaling work that enables technologies to be used in production. So I read a little bit about what you guys have been learning about optimizers. And so, today we're really going to be talking about this particular optimizer Shampoo, which has actually gained a lot of popularity recently within industry. And I think it's also started to slowly permeate out through the rest of the industry in terms of its usage and knowledge. I always like to start these talks by saying that I think a lot of the credit for this work doesn't belong to us directly, but actually a lot of it also belongs to Vineet Gupta and Rohan Anil, who Rohan was originally at Google, now he's at Meta. Vineet is still at Google. So I hope that we've been able to contribute a little bit, I think, towards trying to push these algorithms forward. So I'd like to start also just by asking, why should we even care about optimizers in deep learning? I think if you sort of are coming into the machine learning area, oftentimes what you'll just do is just take Atom from PyTorch or from JAX or TensorFlow and just plug that in. You just sort of use it as the methodology to actually train your neural network model. Oftentimes in a lot of the developments that you see in machine learning tend to be centered around how do we actually think about modeling improvements or scaling improvements as kind of the ways of trying to improve our machine learning models or systems. But I would like to make the argument that actually better training algorithms would ultimately enable us to be able to converge faster to the same model quality, potentially with less data, right? Or enable us to actually obtain higher quality models with the same amount of data or the same number of iterations. This is often because in industry, we don't just worry about, we usually have a limited amount of data that we're also training on. And we're really looking at a single epoch of training with a fixed number of iterations. And one of the major benefits of these kinds of improvements is that unlike model scaling or just continuing to try to change our architectures and make them larger, when we're actually changing our training algorithms, what we're actually doing is we are only modifying the training costs without actually modifying the inference or serving costs. So this can become increasingly beneficial, especially as we begin to hit settings in which actually scaling the model continually actually becomes too expensive to perform inference on, right? I think the other thing that makes Shampoo very unique, maybe as sort of a prototype, not necessarily like the only example, is that it's an optimizer that really begins to move beyond element-wise operations. I think this is something that Shintaro will try to press more into. And so as a result, what happens is that we begin to look at optimizers that suddenly require more memory, that require more compute. They're going to require more complex operations that just go beyond simple element-wise operations. And suddenly we're looking at tensor shape dependence, which has an influence on how we would design sort of the rest of the systems, even around the optimizer itself. So if you look at, I think you guys have learned a little bit about FSDP. You'll actually, I think in PyTorch, there are actually two versions of FSDP that were floating around. And one of them was actually trying to remove the shape of the tensor, right? Another one was trying to preserve the shape of the tensor. And so these are some of the kind of downstream implications of some of these changes that are actually going on within training algorithms that we use in practice. And I think what makes Shampoo very exciting now is that this is really becoming, I think, a more widely adopted state-of-the-art algorithm that's really being used across many places, including Google and Meta. We recently were able to give and show that our implementation actually works quite well also on this external AlgoPerf, ML Commons AlgoPerf benchmark as well. And now there's already these new developments that are coming out. If you've heard of these techniques like SOAP or muon, et cetera, which I think makes this whole area very exciting. So I like to start off just by trying to remind you guys of Adagrad. So I apologize, I'm probably gonna be a little bit more mathematical. I brought Shintaro here because he's the one that really can talk as a systems person, and I'm the person that talks like an ML or optimization person. And I'm trying to give you some systems knowledge, hopefully, in that context. So we'll complement each other in that way. But if you just so you can recall, what is Adagrad? What Adagrad will do is, suppose I have a weight vector that I care about, W here, that is of dimension D, and a gradient vector also dimension D, right? What Adagrad will do is it's going to store an optimizer state that also has length D, okay, that we initialize to zeros. What we will do is we'll aggregate the component-wise or element-wise square of those gradients. And what we wind up doing is we transform our stochastic gradient by dividing by the square root of this aggregate squared sum, right? Plus some epsilon term that we use to prevent sort of division by zero, right? And as I was discussing earlier, like this is actually, you'll see these implementations and they get increasingly complex, usually because of backward compatibility issues or trying to make these things as performant as possible. But if you really think about what is at the core of this algorithm, it's actually quite simple. It can be implemented just in a few lines of code, right? Which, as you see here below, this is sort of the one of the fused implementations of Adagrad that is actually available in PyTorch if you sort of look underneath the hood. Okay. But I also want to make the case that when we actually are doing this, what we're doing mathematically is actually transforming our gradient actually by a diagonal scaling matrix. So if I think about what is really going on mathematically with this particular transformation, what I'm really doing is taking my gradient vector and actually multiplying it by a diagonal matrix, okay, that is going to, where you place actually each element of this VK vector actually on the diagonal of this matrix, and you're taking actually the inverse square root of this diagonal matrix. And simply because your matrix itself is diagonal, actually taking the matrix inverse square root here simply corresponds to actually applying the inverse square root operation to each of these individual components. And then when I'm actually then multiplying, right, this matrix to this vector here, right, I get the result that I actually see above. And this is actually the more sort of general mathematical formulation that we typically would try to think about in the context of designing optimization or training algorithms. One way we can view how methods really differ in terms of the training algorithms is actually in their choice of this, what we'll call a scaling or preconditioner matrix, okay? And how we use this to actually transform our gradient. And of course, these things get more complicated because you can talk also about, what do I want to do with the gradient? Maybe what do I want to do with the weights, with averaging? But if you think at the core of what Adam and Adagrad are really doing, they're really performing this kind of diagonal scaling transformation. And so it turns out that actually back in the day when Adagrad as a method came out, this is by John Ducci back in 2011, actually, it turned out there were actually two versions of the method that he actually had proposed at the time. One version was this diagonal scaling method, which is basically, I'm rewriting here what I just showed you earlier in the previous slide with this part above. But what I could also have chosen to do, this other method he actually proposed, was this version of full matrix Adagrad, where you would essentially aggregate the outer products of the gradients themselves. So the picture is just that instead of actually just aggregating sort of the squared components of these gradients, I can instead take the outer product of each individual gradient and sum them together. But of course, in practice, these things were never really tested because it's frankly too expensive to try to actually store a matrix that is actually, let's say, D by D, right? And then on top of that, do computation that would require sort of D cubed flops per step, right? So The whole benefit of me using a diagonal scaling here is that I wind up using only an optimizer state that has linear memory cost, right, and linear compute at every step. Now, again, I just want to remind you here that when we talk about the inverse square root here, I think sometimes there's a little bit of confusion in that people will take that and think, oh, that just means I take the inverse square root of the elements, right? That's only true when we have a diagonal matrix, right? So when things actually become like a full matrix, or you start to fill in the off-diagonal components, right? We're no longer referring to the element-wise square root, we're really referring to a matrix square root, meaning that if I multiply this matrix by itself, I get the original matrix in terms of matrix multiplication. And the key observation here is that it feels like we're losing something when we leverage this diagonal attograd approach, this diagonal approximation. Because what's happening now is that we actually lose these off-diagonal elements, these pairwise correlations that would capture something about how these different components actually relate to each other of the gradient. Right? And so this is sort of where Shampoo was introduced as kind of a intermediary actually between these two extremes. So the idea behind Shampoo is to say, let me just think about trying to do some kind of sort of off-diagonal kind of preconditioning, but in a context in which I'm only going to consider this within each layer. Okay, this if you implement like an optimizer in PyTorch or in JAX or in these other frameworks, you'll realize that all of these weights you're typically handed actually all of these weights not as a vector, right? But actually as individual tensors, right? A list of tensors that you're actually operating on. Because of course, when we finally have to perform any kind of inference, any kind of forward pass, backward pass, right? That's sort of the natural form of the original shape itself. And so what Shampoo says is, let me try to do something for each of these individual parameters or tensors. And then let me also try to leverage something about this tensor shape in the design of my algorithm. So I'm not going to go into this. I think there's many more references you can go to if you want more information about this. The key property or the key constraint or approximation that we wind up leveraging is a Kronecker product approximation. And what will happen is the main benefit of all of this is that I'm going to be able to operate now on the parameter in its original tensor shape or matrix shape and try to leverage that shape in the design of my algorithm. Okay, so let's suppose now I just isolate, let's say, a single fully connected layer. Okay, this is like a weight matrix with dimensions, let's say m by n. Okay, therefore my gradient is also going to have those same dimensions, m by n. Right, so if you imagine what was d previously for this matrix, I would have flattened this, so it would have been, d would have been equal to mn. Okay, and what I'm going to do now, instead of trying to either construct a full matrix on that flattened vector, or just maybe I would originally store a state that is also m by n and just do element-wise transformations, is I'm going to now store two optimizer states here. One that corresponds to a left matrix transformation that is going to be m by m, okay? And a right matrix transformation that's going to be n by n, okay? So if you think about, again, what would happen previously, if I had a diagonal attograd, right, it would have required me to store mn, right, or an m by n matrix, right? If I did full matrix attograd, I would have had to store m squared, n squared. And so now I'm looking at m squared plus n squared memory cost, right? And at every step, then what I'm going to do is I'm going to aggregate. Okay, L here is going to aggregate G transpose. And R is going to aggregate G transpose G. Okay, what is one way to interpret what is going on here? You can view this as trying to capture some kind of column-wise or row-wise correlations or sums, right? And then what I'm going to do is I'm going to transform my gradient in its original n by n shape by left multiplying and right multiplying by the inverse quarter root of these matrices. And I forgot to mention this earlier, but this alpha here would correspond to your learning rate or your step length. Okay, so this would just be some positive value. So you would actually then update by this transformation here, okay? Now, Similar to Adagrad previously, the major benefits of all these approaches is that L and R here remain nicely symmetric positive semi-definite. And there's ideas of how to generalize these things further. So, well, Shintaro's still on this slide, so he can probably talk even more about this than I can. But one has to also worry, of course, about this matrix root inverse computation. And so, without going into too much detail on this, right, what we have to worry about here really is this, how do I actually compute this matrix inverse root of A, right, of a symmetric positive semi-definite matrix? And perhaps the easiest approach to do this is simply use a symmetric eigendecomposition and take the inverse root actually of the eigenvalue matrix itself. We aim to do this with as small of a modification to A as possible. Of course, I'm hiding a lot of numerical details, but this also, of course, introduces a m cubed plus n cubed cost, right? Which I think Shintaro will talk a little bit more about in terms of how do we actually try to mitigate, ultimately when I do this sort of algorithm, I'm still looking at matrix, instead of element-wise operations, I'm looking at matrix multiplications. And I'm thinking about matrix inverse roots. So this introduces a certain amount of computational cost that's still expensive. And of course, we have to find a way to be able to mitigate this through clever sort of systems tricks in order to make these things fast in practice. So I think Shintaro will talk a little bit more about this. So let me move through these things really quickly and let him get started. So we'll run through this and let him talk here.
Thank you very much. So I think like Michael's discussion or Michael's explanation is more from the ML algorithm researcher, engineer standpoints. My standpoint is more on how to implement them and integrate it in the system. Okay, so Shampoo is actually very great, like without increasing data, without increasing number of, let's say, the cost for inference, we can update the quality. So this is very great, and we should use Shampoo. However, there are some problems in Shampoo. Fundamentally, Shampoo requires more computation. It requires more memory. Also, it uses complex operators like a root inverse matrix, computation, which is very complex. Also, checkpointing, if we need, will be very complex. And also, it exposes much more hyperparameters. There are so many challenges. Let's focus on the first two aspects. Shampoo requires more computation, more memory, how to optimize them. So basically, there's very detailed discussion regarding how to calculate those, but memory, if it's for Adagrad or Adam, we use, let's say, P for the parameter size P, where this P is number of elements. For Shampoo, we need at least 4P plus a little bit more to store some additional stuff. For the computation, for Adam, computational cost is around a P, but for Shampoo, because we need matrix multiplication for this block size of matrix rather than element-wise operation, which is totally proportional to P. It is P multiplied by P, where P is sort of the block size constant. So, fundamentally, Shampoo is much more expensive in terms of memory and computation during training. Let's alleviate it. So there are two optimizations, but let's explain some rough ideas about why, how Shampoo looks like. This is about computation time. The x-axis is basically the timing. On top of it, there's Adagrad or Adam. So after forward and backward, we run optimizer. Every run in this distributed data parallel setting, we do the same computation. However, this Adam optimizer is very, very short. On the upper side, this red one and yellow one, in total, it will be around 1 or 2% of forward backward, depending on models, number of trainers, and everything. However, for Shampoo, it will be completely different. If we just run Shampoo as it is, by, let's say, taking some implementation from the researchers, algorithm researcher, this green part, the dark green one, root inverse computation will be 100x larger than forward and backward. And this precondition part is almost the same as forward and backward. So if we run these on every rank, it will be super expensive, which is not tolerable. To optimize this, there are, roughly speaking, two ideas, two high-level optimizations. The one is precondition frequency. So we cannot really do this root inverse computation, which is like 100 slower than forward backward. We do it every, let's say, X iterations, where X is like 8,000 or 10,000. In that sense, during that X iterations, we will use scale values for root inverse computation. So it will lower the model quality, but this is necessary to make it scale. Otherwise, we cannot really do this shampoo. The second thing is the distribution. So DDP distributed shampoo internally does distribution within the optimizer. The upper side is no distribution. So basically every rank has the same computation and they do exactly the same computation to update parameters. This is pretty much like, affordable for this, simple Adam or something, because this update precondition part is the largest, and then this is only 1% or 2%. If it's shampoo, this precondition part is almost the same as forward backward, so we would like to parallelize it. In this specific example, we parallelize it over 2 GPUs. So in this case, this computation, previously, we do this computation only one rank, and then every rank does the same computation. We parallelize it by doing this computation over 2 ranks. And after doing this, we do all together to update parameters. So this can parallelize this precondition part, but it adds some communication cost. Update parameter is the same because we need to update parameters of every rank. This is sort of the optimization. After doing those simpler optimizations, memory computation convergence trade-off becomes like this. So memory previously originally for P, but it can be divided by N, number of trainers per group. But we also need to add some communication buffer, which has P. Also, how to distribute those computation across ranks is a very different problem. Basically, the granularity is a block. And then if we don't really have enough number of blocks, we cannot really distribute those blocks across all the GPUs. And particularly if you use so many GPUs, it gets really hard to evenly distribute those blocks. So that becomes a problem. For the computation, the same thing. So there are some additional cost and cost. So as a result, if you use large precondition, performance gets increased, but convergence gets worse. So it exposes very complex performance, computation, and convergence trade-off. If we go a little bit more, I think you can instantly come up with some optimizations. One thing is computation communication overlap. I think you've heard of it. If you overlap it, you can hide some computation cost or communication cost. However, and then by using, for example, S stages, you can define S stages and then you can create some overlap. Also, you can optimize this rank block mapping, how to map those block tensors. This is also something that we need to think about. Also, you can think about quantized communication or computation. Everyone likes quantization. We would like to introduce quantization, maybe for shampoo too. Or maybe we can run root inverse computation on the host side, and then maybe we can use that computed data after 10,000 iterations or something. That's another thing. We can offload the task to the host or different devices. We can consider many, many things, but practicality aspects, of course, stability of complex operation is needed, and we definitely need distributed checkpointing to run it in production. Also, after introducing those optimization, it exposes so many hyperparameters that machine learning engineers can't understand. So that's really the problem. So it gets more complex. And then if we expose more hyperparameters, it's making the code much more difficult to maintain. So overall, if you see those optimizations, the system engineer needs to understand those trade-offs plus maintenance cost, plus some explainability to other people so that, you can tell that, this has a trade-off, you should do it, you shouldn't do it. So understanding the whole picture is actually very important to design a system. Distributed shampoo itself is, alleviates performance and memory consumption issues. Yes, it introduces further optimization opportunities like this, for example. However, to become a good, system engineer, it will be great to understand the trade-off and then not introduce all the optimizations that you can come up with as a researcher. Let me pause, and then I think that's the end of this presentation.
Okay, thank you.
Did I take too much time? I